We've now come to our last test for series convergence, and that test is called the ratio test. Now, this test is being presented last because when looking at various tests that you can use to show that a series converges, this is actually the last one that you should consider. If you have an alternating series, then you should use the alternating series test. If you have a geometric series, then you should use a geometric series test. If you have a p-series or something that looks like a p-series, then you should use the p-series test or the integral test. So the ratio test is actually the test that you should use when all other tests fail. And I will point out a few times in which it is helpful to look at the ratio test. So before we do the ratio test, let's review something about geometric series. So we have a geometric series, the sum from k equals 0 to infinity of a times r to the k. And we remember that this series converges if and only if r is less than 1. Now I want you to note that the n plus first term divided by the nth term is actually r. If you take a r to the n plus 1 and then you divide it by a r to the n, in fact, you will get r. So another way to write a geometric series test is that a geometric series converges if the ratio of the terms an plus 1 over an is less than 1, and it diverges if the ratio of the terms is greater than or equal to 1. So r is actually the ratio of the terms, and that's actually why we use the letter r when we talk about geometric series. So we want to leverage this idea that if the ratio of the terms is less than 1, then the series converges, and that if it's greater than 1, it diverges, and to show that other series converge. So what we're going to do is we're going to actually look at the limit of the ratios of the terms. The limit as n goes to infinity of an plus 1 divided by an, all in absolute values, and that's going to determine whether the series converges or not. So we're going to look at two cases. The first is when we can find that limit as n goes to infinity of the absolute value of an plus 1 over an, and that limit is equal to L, and that L is less than 1. So the idea here is we're going to let R be a number somewhere between L and 1. Okay, so we're going to think about R as being greater than L, but less than 1. Then if you go far enough out in the sequence, because the limit is L, it must be that an plus 1 over an in absolute values is going to be less than that some number r. We know that the limit approaches L, but it must be, if you go far enough out in the sequence, that the ratio of those terms is going to be less than some number that's a little bit bigger than L. So we'll call that number r. Well, then we can rewrite. We can say that an plus 1 is less than r times an. So what we're going to do is we're going to multiply by an here, and that's going to give us that an plus 1 is less than r times an. Well, in fact, an plus 2 would then have to be less than r times an plus 1 for the same reasons. But an plus 1 is less than r times an, so that would be less than r squared times an if we substitute in the line just above. Okay. Well, what about an plus 3? Well, that's going to be less than r times absolute value of an plus 2. But we already showed that that's less than r squared a sub n. So an plus 3 is less than r cubed times a sub n. So we're starting to establish a pattern here. We're starting to see that for I being 1, 2, 3, etc., that an plus I is less than r to the I times the absolute value of a sub n. Now what's interesting is that the terms that you see on the right here, these terms are the terms of a geometric series. And they have an r that is less than 1. Okay, so the first term is going to be absolute value of a sub n, but the rest of the terms we're multiplying by r to the i-th power, and here r is less than 1. Well, that tells us that the sum of the absolute value of the terms a sub n must therefore converge by the comparison test, because we are comparing these terms a sub n plus I to a geometric series r to the I times the absolute value of a sub n. And so it follows that our sum without the absolute values actually converges as well, and it converges absolutely because the sum of the absolute values of the terms converged. In fact, that sum converges absolutely. So essentially, we've used the comparison test and what we know about geometric series to show that if the limit of the ratio of the terms is equal to some L less than 1, then our sum converges absolutely. Now, what happens if we get a limit, but that limit is equal to some number L that's bigger than 1? Well, we can say then for large enough n, then the next term would have to be bigger than the previous term. If we're going to get the ratio of the terms to be a number that's bigger than 1, then at some point, the next term must be bigger than the previous term, and then each additional term must be bigger than the term before it. And so the sequence of terms, a sub n plus 1, a sub n plus 2, etc., is actually strictly increasing. Well, if we have a sequence of increasing terms, okay, then the limit of that sequence of increasing terms, not just increasing terms, but increasing positive terms, cannot be 0. And so that means that the series diverges. And it diverges because the terms don't go to 0. It diverges by what we called the nth term test. Okay, so this gives us a second case for the ratio test. It says that if the limit of the terms is some number L that's bigger than 1, then the series must diverge. And so now I want to put all of these together so that we have the ratio test for convergence. So we have a series, the sum from n equals 1 to infinity of a sub n, and then we're going to let L be the limit of the ratio of the terms a sub n plus 1 over a sub n. Okay? If L is less than 1, the series converges absolutely. So if the limit of the ratio of the terms is less than 1, then the series converges absolutely. But if the limit of the ratio of the terms is bigger than 1, then the series actually diverges. Now, unlike geometric series, if the limit of the ratio of the terms is 1, then the test actually doesn't give enough information Okay, it does not tell us whether the series converges or diverges. That means that there are going to be some series whose limit of the ratio of the terms is 1 and the series converges, and then there's some for whom the limit of the ratio of the terms is 1 and the series diverges. So let's do a couple examples, okay? So when do you use the ratio test? Well, you use it when things look kind of geometric. So what I have is a series n over 2 to the n that would be geometric if it was 1 over 2 to the n, but is not because it's n over 2 to the n. So it's kind of geometric. So what we're going to do is we're going to take the limit as n goes to infinity of the ratio of the terms. So we're going to write the n plus first term, which is n plus 1 over 2 to the n plus 1, divided by the nth term, which is n over 2 to the n. And what we need to do is essentially simplify this quotient to find the limit. So I'm going to multiply by the reciprocal. So I'm going to get n plus 1 over 2 to the n plus 1 times, and then I'm going to get 2 to the n over n. Now, 2 to the n cancels with 2 to the first, or 2 to the n plus first. It's leaving me just with a 2. So I'm going to factor out that 2, and then I'm going to get the limit as n goes to infinity of what's left, and that's going to be n plus 1 over n. So I now take the limit. I'm going to get 1/2, and then the limit of n plus 1 over n is 1. And so my limit L is 1/2, which is less than 1. And so then I can conclude that the series converges absolutely. Now, I don't really need to say absolutely because all the terms are positive, and so that's kind of obvious. But again, that is generally what you can say. So the series converges absolutely by the ratio test. Okay, another instance in which you can show that a series converges by the ratio test is when you're dealing with factorials. Okay, whenever you're dealing with factorials and in your sum, it is good to use the ratio test. So we're going to take the limit as n goes to infinity of the ratio of the terms. In this case, it's going to be 2 to the n plus 1 over n plus 1 factorial divided by 2 to the n over n factorial. And again, in the denominator, we're going to want to instead multiply by the reciprocal. So we're going to get 2 to the n plus 1 over n plus 1 factorial times, and then I'm going to get n factorial over 2 to the n. Now, again, I can factor out a 2 because here 2 to the n plus 1 is going to cancel with 2 to the n, leaving me just a 2. And so I'm going to get 2 times the limit as n goes to infinity of n factorial, and then n plus 1 factorial, which is n plus 1 times n minus 1 times n minus 2, etc., can be written as n plus 1 times n factorial. And so you'll see that the n factorials cancel. And so I'm left with the 2 times the limit as n goes to infinity of 1 over n plus 1. And so that limit is going to be 0, which of course is less than 1. And so we can say that the series converges. We can even say absolutely if we like, although all the terms again are positive, by the ratio test. And so these are two examples of how to use the ratio test. Now, in both cases, we had that the series converges. Obviously, there are going to be times where the limit is going to be greater than 1 and the series diverges. What happens when the limit is 1? Well, Let's look at two particular series. First, we're going to look at a p-series, the sum of 1 over n squared. And does the series converge? Well, yes. Okay, that's a p-series, right? And p is 2 in this case, which is bigger than 1. But what is the limit of the terms? Well, the limit of the terms, or the ratio of the terms, excuse me, is 1 over n plus 1 squared divided by 1 over n squared. And so we want to simplify that limit. Always good to remember to write your limit signs. Okay, so that's the limit as n goes to infinity. Okay, multiplying by reciprocals, that's actually going to be n squared over n plus 1 squared. Now, looking at that limit, okay, the numerator has a power of n squared, the denominator has a power of n squared, and so that limit is 1. So here we have an example of a series that converges even though the ratio of the terms is 1. Well, what about the series 1 over n? That's the harmonic series. Well, that we've seen that series does not converge. Okay. So that series doesn't converge. What is the limit of the ratio of the terms? Okay, so that's the n plus first term is 1 over n plus 1. The nth term is 1 over n. That limit, if we simplify it, is going to be n over n plus 1. And so that limit is actually going to be 1. But now we have a series that diverges, but the limit of the ratio of the terms is 1. So we can see that if the limit of the ratio of the terms is 1, sometimes the series will converge and sometimes the series will diverge. And so this is why I say if you have series that are p-series or look like p-series, you really can't use the ratio test. You need to use a p-series test or the integral test. And so the ratio test is really no good when you're dealing with series that look like p-series.